In this lesson, we will be picking up a new integration method called integration by parts. It's used specifically for integrating products. Essentially, what we're doing today is undoing the product rule for differentiation, and this provides us a method for integrals that can't be evaluated either just by simplifying the integrals or by using a u substitution. So for example, here would be an example of an integral that can't be integrated using our traditional method. So if I want to take the integral of x e to the x. So how this is different than maybe what we've seen is there isn't anything that can really be simplified to just use a basic integration rule. There's no good choice for a u that would make this any easier to integrate. Because if you had your u be x, it would still just be u times e to the u, which isn't any simpler than what we have there. If this was something similar to what we've done in the past, perhaps using a u substitution, our setup would look something a little more like this, where your u could be x squared and your du would be 2x dx. All right, so let's get going then into what integration by parts is. It uses some different letters for variables than we've used in other lessons this year. So we are using u and v. So I just want to start off with maybe differentiating the product u and v just to kind of get used to what that would look like to help us with the formula that we're going to learn today. So if I have the product of u times v, and I want to take the derivative of that, if you recall by the product rule, order is not important, but one way you could take the derivative would be v times the derivative of u plus u times the derivative of v. Another way to think of that would be, instead of writing u prime, you could think of that as du, and v prime is dv. So this is going to be very similar to the formula that we're working with today. So maybe you're more familiar with doing product rule with an actual equation. So just if the previous example wasn't helpful, let's just take a quick look at this. The derivative of y equals x e to the x. So the derivative of x is just going to be 1, so I'm going to have e to the x plus x, and the derivative of e to the x is just e to the x. So again, you can see those different parts there. All right, so let's see where we're going with this. So let's say I have that derivative of uv prime is still equal to v du plus u dv. All right, so we want to use this for taking the antiderivative. So we take the antiderivative of each of these parts. The antiderivative, the derivative of uv prime is just uv. And then I'm going to leave these with the integral sign there. So what we're going to be starting with today is that we'll be identifying the u and the dv, and then we'll be subtracting over the v du. And so we'll be working with this part of the formula today. So when we look at an integral, we'll be identifying the u and we'll be identifying the dv, and I'll give you some strategies for choosing those. And from there, you'll be using the formula u times v minus the antiderivative of v du. So once I've chosen dv, I'll need to identify what v is. And then the integral v du will hopefully be one that's easier to integrate than the one that you just got, assuming that you chose your u and your dv correctly. So the formula that you need to know for today is the antiderivative of u dv is equal to u times v minus the antiderivative of v du. All right, so let's go back to that example that we started with at the beginning of the lesson, the x e to the x dx. So just for this first example, I'm just going to say my u is x and my dv is e to the x dx. Again, I'll give you some strategies as we're working for how to choose those, but let's just start with this just so you can get familiar with how the formula works. So if u is x, du is the derivative of u, so 1 dx. If dv, or the derivative of v, is e to the x dx, I need to take the antiderivative to get v. The antiderivative of e to the x is e to the x. All right, so then I just identified this part. Here's the u dv. So now I need to determine u times v minus the antiderivative of v du. Okay? Well, u times v, u is x, v is e to the x, and then v du would be this, so minus the antiderivative of e to the x dx. uv is still just uv. The antiderivative of e to the x is e to the x. So then that's how I use integration by parts to integrate this. All right, so let's look at another example. So I have x squared natural log of x dx. So as promised, I'll try to give you some strategies for identifying which is the u and which is the dv. One of the first criteria that you have for choosing is when you decide what your dv is going to be, it needs to be something that you can actually take the antiderivative of. I don't have an antiderivative rule for natural log of x, so I can't choose that as my dv. So my u has to be natural log of x. And then I'm going to make x squared dx my dv. So when I take the derivative of natural log of x, I get 1 over x dx. When I take the antiderivative of x squared, I get 1/3 x cubed. All right, so I'm going to have u times v, so 1/3 x cubed natural log of x minus the antiderivative of v du. So if I want to multiply those together, I'm going to bring the 1/3 out front. X cubed times 1 over x just turns into x squared dx. So 1/3 x cubed natural log of x minus, this is going to be turn into 1/3 x cubed here, so I'm going to have 1/9 x cubed plus c. So the first rule that I gave you then is when you're choosing your dv, it needs to be something that you actually can take the antiderivative of. And I would also add in that you can take the antiderivative fairly easily, that it's not more complicated than what you're trying to take the antiderivative of in the first place. All right, so if I have x sine x dx, all right, so both of these are things that I could easily take the antiderivative of. So how do I choose what's going to be the u and what's going to be the dv? Well, another criteria that you can have for choosing is what you choose for your u. When you take the derivative, you want it to become something simpler. You want it to become something simpler. So if I choose x for my u, the derivative of that is just 1 dx. My dv, if I make that sine of x dx, and I take the antiderivative, that's going to be negative cosine of x. When I choose something simpler for my u, that should make a simpler integral for my v du. So again, just to kind of recap on the criteria that I gave you, you want to choose something for your dv that you can take the antiderivative pretty easily. And when you choose something for u, you want it to be something that when you take the derivative, it becomes simpler to allow the integral of v du to be something that you can take the antiderivative of pretty easily. All right, so then I'm going to start with u times v, so negative x cosine x minus the integral of v du. I'm going to do minus a negative, so that would become a plus cosine of x dx. All right, so negative x cosine of x plus sine of x plus c. Okay. It will be possible that as you're doing this, you might end up sometimes picking the wrong u and dv. So on this example, I just want to show you how you would identify that you know that you picked wrong. So what if we had chosen the other way around? So we had said that this was going to be sine x and this was going to be x dx, just so you can see what I mean by it. You end up, when you make the wrong choice, you make the problem itself more complicated. The derivative of sine is cosine x dx, and the derivative of, or the antiderivative of x would be 1/2 x squared. So if I were to do my u times v, I'm going to have 1/2 x squared sine of x minus 1/2 x squared cosine of x dx, and then the antiderivative of that. So notice that this integral here has actually gotten more complicated than the original, so that's how you know that you chose u and dv incorrectly. just wanted to at least show you that so you can help to better identify what your u and your dv are going to be. Alright, so let's try another one. So I have the natural log of 4x dx. So I can't take the antiderivative of natural log, so my u is going to have to be natural log of 4x. It's possible for your dv to just be 1 dx, as long as all of the parts that are here are covered in your u and dv. The derivative of natural log of 4x will be 1 over 4x times 4 by chain rule. The 4's will end up canceling, so it just ends up to be 1 over x dx. The antiderivative of 1 dx is just x. So when I go ahead and I integrate that, I end up getting x natural log of 4x minus, and then the product of v du, x times 1 over x is just 1. So x natural log 4x minus x plus c. Alright, so now I have x squared cosine of x dx, so I would start this similar to the other example that I had with x sine x. My u is going to be x squared because I want to pick something that when I take its derivative, it's going to get less complicated. So my v is going to be sine of x. Alright, so let's go ahead and write this out. So I have uv, so I have x squared sine x minus, I'm going to bring the 2 out front, x sine x dx. Alright, so taking a look at this, this is something here that I can't take the antiderivative as is, but it is considered simpler than what I had up here because the power or the degree on x is less than the original. So it is possible that you may have to do integration by parts more than once. So what I'm going to need to do is I'm going to need to do integration by parts to evaluate this integral. The only thing that can really maybe be a common error on this is sometimes people then will forget the other parts that we had from the original problem, so don't forget to include those in your final answer. But now we need to pick a new u, du, and v and dv. Alright, so I'm going to go back with my x. The derivative of that is 1 dx. Sine of x is my dv, so negative cosine of x is my v. So this will carry down. I don't really do anything with it. And then I'm going to have u times v, which is negative x cosine of x. And then minus, so it becomes a plus, then the antiderivative of cosine of x dx. So x squared sine of x plus 2x cosine of x minus 2 sine of x plus c. Alright, so let's go ahead and look at one last example. So I have the antiderivative of 1 over x and the natural log of x quantity cubed. So just to kind of go through here, I can't take the antiderivative of natural log, so I probably want to make that my u. And then that's in the denominator, so it's going to need to have a negative 3 power on it. My dv then I guess would need to be 1 over x dx. So when I go ahead and do my du, then it's going to be negative 3 natural log of x to the negative 2 times 1 over x. And the antiderivative of 1 over x is natural log of the absolute value of x. So when I do my u dv, I end up with natural log of x to the negative 3 times natural log absolute value of x minus a negative antiderivative of v du. So we have 3 natural log of x to the negative 2 times 1 over x times natural log of absolute value of x. So this got quite a bit more complicated. I mean, this will simplify a little bit, but I wanted to do this example just to remind you of perhaps not every integral that you do can be integrated by parts. There are some integrals that can be evaluated more than one way, but parts should really be a last resort for you. You should always try to simplify the integral first, try u substitution, and then if those aren't working and it's not a rule that you have, like an inverse trig rule, then try integration by parts, because this problem is actually much simpler done just with a basic u substitution. So I actually wouldn't do parts at all, even though that this technically could be simplified, but this wasn't the most efficient way to do this problem. So if you would have had just done this with a basic u substitution, your u would have been natural log of x, the derivative of that being 1 over x dx. So this just becomes a 1 over u cubed problem, or u to the negative 3. So then when I integrate that, it goes up to u to the negative 2 with the negative 1/2 out front. So negative 1 over 2 natural log of x quantity squared plus c. All right, so just to do a quick recap, integration by parts should be used after you've already tried to see if the problem can be simplified or if a u substitution can be applied. When you're choosing your dv, you want to choose something that you can take the antiderivative of easily. And when you're choosing your u, you want to choose something that when you take the derivative, it becomes something simpler.